Well, thank you very much. Can you hear me well with this mic? It's a great pleasure to be here and to have this opportunity. And while I was preparing these slides, I was thinking about the story of the two scientists that are arrested during the war, and they were going to be executed, but they were given a last wish, and then one of them said, I've been working on all this work. I want to organize a meeting and tell the participants everything we have done. And say, okay, you get that wish granted. And then they asked the other scientist, what would you like, last wish? And he said, I would like to be executed before that conference. So this is a little bit like that. This is work we've done over the last 4 years, and as part of the CCI, which is a NSF Center for Quantum Dynamics and Quantum Computers, that I initiated at Yale in collaboration with science and in the Applied Physics Department, including Michel, who just won the Nobel Prize, and Ethan Geva from University of Michigan, Lea Santos from University of Connecticut, and Sabri Kais at that time was at Purdue, and now he's at North Carolina State. And what we face at the moment, at that time when we started with this center, is that there were lots of resources for running quantum algorithms on quantum devices, such as Qiskit, which is a fantastic resource, as well as platforms for simulations on classical computers like QTIP, but is also another fantastic resource. But understanding what is under the hood in the functionalities of those packages, or integrating in a single code, a classical simulation baseline with the quantum corresponding simulation, was very difficult. And my students had a hard time understanding what's going on under the hood of initiate, when you initiate your state vector with Qiskit, because that documentation is not provided. And so one has to go through all of the papers of the algorithms that were developed and which ones were implemented. So the intention of this presentation is to provide all that to you in the form of an explanation, slide by slide, and also all the software for actually implementing those snippets that demonstrate those functionalities in a common framework, which we call QFLAX. So basically, this is a software package that we developed to integrate the various different resources under the same umbrella, so that we can offer simulations that are system-centric, in the sense that you define the Hamiltonian, you define the observables, you define the initial state, and then you have options for various different types of simulations, whether you want to do it on a qubit-based computer with a quantum circuit, or you want to do it with an ODE solver, or if you want to include dissipation or not, whether you want to put temperature. It can all be done on the same code and the same framework. So that's what I'll be providing. And here I provide the links. So if you click on these link that I already provided in the drive, you go directly to the web page of these of QFLAX, where let's do that experiment. I didn't practice this, but I'll do it here to see whether I can come back to this page. So you come here, and you see you have the various different options from installation and all the Jupyter notebooks that allow you to run everything I'm going to be describing in Colab simply by clicking on these notebooks and hitting run all or run whatever cells. The cells need to be run sequentially. And my intention this morning is to go over these 6 notebooks. It's a little bit ambitious, but in any case, I will provide all the materials, including all the slides. so that whatever we don't manage to cover, you can go through it and get in touch with me with questions. This repository also provides all the codes. So for any one of the functionalities, and it's intended to be an open source code. So if you want to contribute, there are instructions on how to contribute to this repository. I understand that in this workshop so far you haven't had any hands-on part. So hopefully this will recap a lot of the ideas you discussed so far and demonstrate how to actually implement it in concrete examples. And the examples I've included here are the simplest possible examples, rather than talking about the most complex possible applications of quantum dynamics. Here, what is the benchmark harmonic oscillator two-level system that you can demonstrate with whatever algorithm you are implementing, and compare to a baseline that demonstrates that your setup is correct and that the results are not accidents, but they are agreement because they are correct, right? So that's a little bit of what this presentation is all about. Also, in 6 parts, for each part I have here the corresponding notebook from that web page. Also, for each of these 6 parts, there is a whole paper that hopefully I'll be able to send you the link as soon as they are uploaded to the archive. So anyways, the first part is, and they told me that if this happens, anyways, since I'm staying here, I can come back and do it by hand. This first part, so this is the paper that for this first part that is focusing on intuition and classical foundations. So building intuition and classical foundations for classical dynamics. So instead of assuming that we are all experts, I'm assuming that we know nothing and we are starting from scratch. And so the first thing is how to actually do quantum dynamics for a system and how to do it with a classical computer in the most practical and reliable way. And why to engage in a simulation of dynamics or quantum dynamics is because dynamics underlies spectra. If you want to understand spectra or transport or coherences, relaxation, anything in chemistry or physics relies on, can be understood and simulated and modeled by in the dynamic simulation. Also, any quantum circuit is a dynamical process. It's a quantum dynamics process. So even when you are computing properties at equilibrium, you're solving a dynamical problem of the quantum state vector that is prepared through the circuits through a sequence of transformations in time until you make the measurement. So basically, the methods that are applied here apply to any problem in quantum computing or any of these problems in chemistry and physics. But the problem is that all these problems scale poorly because the Hilbert space is exponentially large, and therefore you can only do with classical computers what you can afford on the memory of the device, which is usually very small systems, or even when you can model, for instance, molecular dynamics of billions of particles, you still hit a wall because the space eventually, since the problem scales exponentially, eventually you don't have enough memory or resources. So that's why implementing Hilbert space in a very compact form, in the form of a quantum register, is the best way to go. And now we have all the methods available for doing that, and we have the computers. The only issue is that computers are noisy, and therefore we cannot actually run them for too long. But that problem is currently being addressed and will be soon solved with correcting for the errors in the same way as the errors are corrected on these computers, on the classical computers. without those redundancies and correction protocols, this computer wouldn't be doing this at this moment, because it has billions of transistors that are failing constantly. So another aspect that is very important is that we need baselines. We need a way of simulating this with a classical computer, and at least for a very small system, show that the quantum circuit and the classical as simulation agree. So, so that's what I was talking about this having a common framework, common architecture for a software that allows you to do that. The problem, as I mentioned, is that the current ecosystem is fragmented. So you have, for instance, QTIP, MQSQD, tensor networks for a variety of packages for tensor network simulations. Some of them you might have covered in a previous talk, Qiskit circuits. But having access to all of these concurrently is challenging and is not available. So QFLAX offers that possibility.
That's a quick question.
Sure.
So you did mention that the Penny Lane package. How do you think about that package?
Yeah, Penny Lane is a fantastic package, and we have a beta version where we have Penny Lane. We also have Strawberry Fields and Bosonic Qiskit, but in the current version that I have here in this web page, we haven't included that. Yeah. So anyways, this is, as I mentioned, it's an open source Python framework. You can contribute, and supports both closed systems that evolve according to the time-dependent Schrodinger equation, or open systems that evolve according to quantum master equations, like Lindblad or generalized quantum master equations, and integrate classical tensor networks, quantum circuits in a single architecture. And the emphasis is on validation and cross comparisons. That is something essential in any development. You always need to do that in order to know that what you're doing makes sense and you can go to the next step. It's model-centric, as I mentioned, with the same Hamiltonian initial state and observables. Select the back end if you want to do it as a closed system, if you want to do it as an open system. And so this is the design strategy of QFLAX. So as I mentioned, it includes 4 modules. One is closed systems that evolve according to the time-dependent Schrodinger equation, open systems that develop and evolve according to quantum master equations like Lindblad or GQME. And then another one that is GQME, that basically this is for systems where the bath has memory, and therefore you cannot use the Lindblad equation. Or that the coupling between the system and the bath is too strong and it goes beyond the approximations of Lindblad, and variational methods that make these implementations friendly to current devices that have noise. And so as you see here in red, we have the dependencies that, so if you install QFLAX, you're installing all of these at the same time, and you don't need to install anything else. People install QFLAX, and you might have to import functions from these packages, but you don't need to install them. And so with this in mind, now the process, the workflow for quantum dynamics is always the same. So you initialize the state, you propagate it with whatever form of propagator you want, and you compute observables. That stays the same no matter what type of simulation you're performing. And you have the same workflow for both classical simulations and quantum simulations. As a refresher for you on closed systems, so these are the evolution of pure quantum states that evolve according to, as a wave function that evolves according to the time-dependent Schrodinger equation. All what you need to do is to multiply the initial state vector by these propagators. So this is a matrix. So you do matrix vector multiplication and you obtain the final. So if you represent this as a quantum circuit, that's it. You have that corresponds to the matrix of the time evolution operator. And then at the end, when you have that state vector, you compute observables as expectation values or correlation functions that give you access to observables like spectrum. So a very convenient baseline is to solve this time-dependent Schrodinger equation, which is a first-order ordinary differential equation, with an ODE solver like Runge-Kutta or any of the available ODE solvers that have been developed over the decades. How you do that? You start with the Schrodinger equation. You substitute the wave function in terms of a basis. So here you choose a basis. It could be a Fock basis, and it could be any basis you want. For instance, Q-tip uses coherent states as a basis. And when you substitute this into the Schrodinger equation, you transform the Schrodinger equation into this ODE. So there is evolution of the coefficients, C of t, that now can be solved with an ODE solver in a conventional way. One is, for instance, Runge-Kutta. So you simply update those coefficients from the previous values of those coefficients with this update that is defined by this coefficient for a given integration time step. This is under the hood of SciPy, for instance. So SciPy has Runge-Kutta 4.5, does exactly this, computes these coefficients, replace here, and updates the coefficients in one step. Then compares these two coefficients to give you this delta that defines how you adapt the integration time step. So you have a very accurate simulation of dynamics. Yes?
Is this in the spirit of ED? Is this in the spirit of ED?
TD, time dependent.
Exact diagonalization. So you have a full
exact diagonalization. Okay, so I got it. So the exact diagonalization is another way of solving this. Instead of solving this equation, what you solve instead is the time-independent Schrodinger equation, where you have h psi equal to e psi. With that, you get the eigenstates, and with the eigenstates, you build a superposition like this one. And since the eigenstates evolve according to their eigenvalues, you obtain the time-evolved state, analytically. You don't have to run any, but yeah, they're connected. Yeah.
So the question was rather if the Hamiltonian is a big sparse matrix, or if it already has structure. If there's no trotter here.
This is completely general. There is no assumption of the structure of the Hamiltonian. Yeah. So, yeah.
Does the Runge-Kutta iteration preserve unitarity?
So approximately, yes. And so that's why you have to adapt this step to have numerically accuracy as much as you want. Yeah.
Are there better? There are better algorithms that work.
Sure, there are many algorithms. I've given one that is very convenient and simple to implement. But I'll talk about another one that is symplectic and addresses that issue that you're describing. Here, I'm not trying to demonstrate everything I know or everything we know. I'm trying to walk you through, assuming that you know nothing and you learn things that you can actually use and implement one step at a time. So how you demonstrate that this method works, let's, in the simplest possible example is an example you can solve analytically, like the harmonic oscillator, for which you can actually compute analytically the evolution of the quantum state, and also you compute observables x and p as a function of time, and you can do it analytically, and you can do it with Q-tip using one of these ODE solvers. And you confirm yourself that the setup of your code, if you run this code in section 2 of this notebook, you get exactly this picture, and that the results from Q-tip are correct because they match the analytical results. So finding a benchmark for which you have an analytical result in any project is essential to validate your methods. Then you can modify the potential to any complicated potential you want for which you don't have analytical results, and expect that the setup that you have is sufficiently good. So another way of solving this problem that connects nicely with the concept of a quantum circuit is what we call the split operator Fourier transform method, which is also called trotterization, one form of trotterization. has been known for a very long time, since the 80s, where you take that time evolution operator that I described before, e to the minus I h over t, and you, for instance, for this problem of a harmonic oscillator where the Hamiltonian splits into a part that depends only on momentum and another one that depends only on coordinates, and you approximate that e to the minus I ht by a product of e to the minus I p squared over 2m t and e to the minus I b t over h bar. If you want to do it to second order, if you want to do it to third order, you do a half full step and then another half. And then it's an approximation because these two operators don't commute, right? So here you have, if you split the, remember what the time evolution operator looks like here. Sorry, that should have included that. Thought I had it here. So this was the time evolution operator that we have to apply, right? So if you split it into this way, you have 1/2 of this part, a full integration for that part, and then another half. So if you have an initial state vector, all what you need to do, and it's represented in coordinate basis, all what you need to do is a multiplication of this function of x with this function of x. Applying this operator, however, is in momentum space. So if you want to do it as a multiplication, you have to transform this function of coordinate into a function of momenta. And for that, you apply in a Fourier transform. And then we can do it just by simple multiplication. Fourier transform back. Now you have all this in coordinate representation. You apply the other half. And this is accurate to third order in tau, in this time integration step tau. So this is very accurate. It's a little bit stiff, but it's always a fantastic result. And it's a wonderful classical baseline that you can implement. Yep.
Sorry, you mentioned this, but I didn't get it. So what do you do the first round of Fourier transform?
So this one is to transform this function of x into a function of p. So now you can multiply this operator.
Okay, so then.
And
so does that help with non-commutivity?
Right, these two are not commuted.
Yeah,
so
that's why.
So the error is proportional to the commutator of the two, and times this tau, and actually tau squared, and then you have to make tau sufficiently small to neglect that error, but this works quite well. Now, this is not only a wonderful baseline, but also connects with what we're going to see next, which is the implementation of quantum circuits. Because as you see, this is the operator that can be described by a quantum circuit that applies onto the state vector, right? So the structure of these, it introduces a structure of operators that correspond to quantum circuits that you concatenate in a quantum circuit. And also the Fourier transform can be efficiently implemented with a quantum Fourier transform in quantum circuits. And therefore, this allows you to propagate things. So the overall structure of this evolution is simply like this. If you are considering an initial state, initialize from vacuum, you initialize with this circuit, prepare the state vector at time 0, then you apply the sequence of potential, Fourier transform, kinetic, potential, and first inverse Fourier transform and potential, and you do one step of the soft method, right? So at this time, you have propagated the initial state to time tau, and you repeat this, so you put many of these circuits together, and you get, you can compare now with not only with the analytical result, again, for the same harmonic oscillator, that this method actually works, and is quite powerful. So, anyways, in this section 3, you have the actual implementation of that on a classical simulator. Now, beyond pure states, you must have heard already the presentation of tensor networks is that we have systems that are mixed. That means that you cannot represent them by a single wave function. So you can only represent the system by an ensemble of wave functions, which is called density operator. And those systems might be at finite temperature and might be interacting with environments, and and you need those density matrices and the propagation of those density matrices instead of propagating a state vector. So that's the unfortunate reality, that the time-dependent Schrodinger equation doesn't describe reality, because reality of any system is a system coupled to an environment, and that environment always induces dissipation, and the evolution, in fact, is non-unitary. And since the evolution is non-unitary, we have a problem, because quantum computers only implement unitaries. So you have to think about how to implement non-unitaries with unitary transformations. So we're going to be talking about that. That is describing mixed states dynamics. And here you can do that with a classical implementation. So the trick for doing that is to enlarge the Hilbert space, double the Hilbert space, so that now you have the system and the environment all in a pure state. And then you trace out the environment, you get the reduced system that you're interested in, which is dissipative. But since you have to enlarge the Hilbert space, you need powerful methods for the propagation. Therefore, this grid-based representation of this basis representation that I just described is not good enough, and you need to make, to implement these tensor network methods, such as the tensor train thermal field dynamics that I'm going to be using here. So with that, in that way, what you do, maybe if you remember from the previous talk on tensor networks, you approximate your density matrix, or you in this case, or you can also do it with a wave function, you represent it as a sum of product of matrices. And you never actually compute the product of the matrices. You keep the matrices always, and you update those matrices. And whenever you compute an observable or an amplitude at a certain point, you do the specific multiplications that lead you that, but you never reconstruct the whole object in the full-blown Hilbert space, or dual space in this case, because that will always kill your code and would crash because of lack of memory. So that is, and then what is nice about this approach, the thermal field dynamics, that you can read also not only in the tutorial papers that I circulated, but also in previous publications from my group, is that you can describe now the Liouville equation, for instance, for the evolution of the density matrix, as a Schrodinger equation, where the wave function depends on temperature. So basically, you can rewrite this matrix by vectorizing this matrix. So you put all the elements of this matrix as a big array, and the superoperator is matrixized. So you build a matrix out of this superoperator that applies, describes the evolution of the system, and you rewrite it in this way. And this is an exact transformation of the Liouville equation into a thermal Schrodinger equation. And this Hamiltonian, in fact, is the Hamiltonian of the system expanded with a space of fictitious variables that are copies of the real variables. And then you have the corresponding symmetric part of this Hamiltonian that you have, which correspond to the Hamiltonian of the fictitious variables, for which you can use any Hamiltonian, including Hamiltonian equal to 0 for that, so you just keep this one. So, so in this way, we are back to the propagation of the Schrodinger equation. You can use a linear solver, you can use soft or other ways. The initial state, you have a thermal density matrix. This one can, when the system is coupled to a harmonic bath, this state can be prepared very efficiently with a squeezing transformation that allows you to also make this propagation very, very efficient. Anyways, for these, as I mentioned, the way to implement this Schrodinger equation in dual space with real and fictitious variables is to use tensor networks. So what we use in this package is a tensor train representation, and the evolution with this matrix product state representation can be based on a trotization that is called time-involving block decimation in the physics community. So this is a very practical approach for short-time dynamics. It's numerically exact dynamics when the rank of this matrix is sufficiently large. And when it's not large, you detect that. When it's not, when you require a matrix that with sufficient rank that is beyond what you can do, you know that because the dynamics becomes very stiff. But there is a problem that you are trying to solve with a classical computer, a problem that requires a Hilbert space beyond the limits of your memory. But you see, this is a representation of that state vector now as a sum of product of matrices. Yes?
You include symmetries here?
Symmetry could be included, yeah, or not, yeah. It's an option.
So that you can have Yale side?
What's that?
Yale symmetries? What type of symmetries?
The type of symmetries that you impose have to do with the representation of the initial state. So you build that in the initial state, and that initial state can be often built as a Kronecker product of those elements that fulfill a given symmetry. And then the evolution preserves that symmetry, according to this type of Hamiltonians.
But the symmetry is not built into the wave function.
No, it's not built into the wave function. No. So with this approach, this section demonstrates how to solve this problem. A spin boson model that many of you love, because you're a physicist. And so a two-level system coupled to a harmonic bath, and demonstrates that at finite temperature the system is dissipative, and therefore in this case the observable decays because of dissipation. Is two-level system in our community is also a qubit coupled to an environment, and that is what you have in any quantum device, qubits coupled to a device. So the takeaways from this part is that classical methods are not just baselines, but prototype for quantum circuits because of the soft approach. They provide this operator structure that matters for subsequent implementations on quantum devices, and that Q-Flex provides a uniform, a connective tissue between these various different ways of simulating. So I hope you will play with this notebook. You will walk through, and also with the document, with the paper associated with it, and you will enjoy an introduction to the classical foundations and baselines. What comes next is quantum circuits for closed systems, doing this on quantum devices, and then we will have hopefully a description of what is going on with the algorithms that are necessary to prepare a state and to implement a unitary decomposition. How do you write a circuit for an arbitrary unitary? What are the methods available and what Q-Flex offers? And then we will go into open systems that involve Lindblad dynamics, variational methods, and non-Markovian dynamics with GQME. So with that, I would like to know whether there are any questions for this first part. Yes?
What's the scale of the problem the classical computer can solve at this point, using, for example?
Yeah, it's not so much the size of the problem what determines what can be solved on a classical computer, but the level of complexity of the dynamics as determined by the level of entanglement. So for instance, this computer can propagate a spin chain with 2,000 spins in 20 seconds or less, so long as the coupling is nearest neighbors only. And but if I put second nearest neighbors and then strengthen the coupling a little bit more, I cannot do more than 24. So that's the kind of, and I can show you, we have code for doing that. Yes.
Could you please, going back to the section where you mentioned the thermofield dynamics, and I didn't get the part where you went from like H to this kind of H bar, this kind of extended with fictitious variable.
This thing?
Yes, this part. Could you please give a bit more intuition on this?
Yeah. In the paper, I described the derivation of this equation in detail from this one. So what you do here is, you see, here you have two sets of variables because you're in dual space. And so what you do is you have a wave function now that depends, let's say, not only on x, but also on x tilde. X tilde is that fictitious variable that is a copy of x. And x and x tilde now don't evolve just with this Hamiltonian, but evolve with this Hamiltonian, which is a component where you tensor product the real variables onto the complete Hilbert space, and then plus a term that involves the fictitious variables. And one can show that if you do this and you compute expectation values of any observable with this thermal wave function, you compute exactly the trace of rho times that observable. And I showed that in the paper, in the tutorial paper. So this is exactly, there's no approximation of the equivalent to the Liouville equation for the whole system. Yes.
Sorry to harp on this point. What is the physical meaning of a variable like x tilde? Why is this introduced?
Yeah, so this is represents the bath of the system in a numerical way. It's not equivalent to a bath because the variables of the system are the variables x. And if you have a system with a bath, you're evolving them according to the Liouville equation, they're all x. But what this expanded Hamiltonian gives you is the possibility of introducing the evolution of the Liouville equation as a Schrödinger equation by vectorization of that matrix into a state vector. Mm-hmm.
What is the H tilde we use and how do we get it?
Yeah, H tilde is arbitrary. You can make a copy of this or you can make it equal to 0. So the results don't depend on H tilde.
Like this, the H, new H appears to be an tensor product of the system and the bar. But how do we incorporate maybe interactions?
Yeah, so think that what we are evolving here are elements of the density matrix. So and this is the complete density matrix that includes the system and the bath coordinates. So they are all included already here. So when you vectorize, you get them all bath and system coordinates in the coordinates of psi.
So what is the explanation for the minus sign?
Which minus sign?
In the H bar, when you in the enlarged Hilbert space.
This one?
Yeah.
Yeah. So, and this is simply that you can demonstrate that if you subtract this term, now here you can put an arbitrary Hamiltonian. So this is the most general form of that expanded Hamiltonian that you need in this thermal Schrödinger equation. This has been done like 20 years ago, and it comes from the condensed matter physics field, now implemented in the realm of tensor networks quite extensively by many groups, and including this. So the theorems that show that are, we also do that in that tutorial paper that. Yes.
So, why do we assume that this is a purification technique? Like psi still a mixed state, and it depends on temperature and everything.
Yeah, we call it purification because we are converting this equation into a Schrödinger equation. So now you have a single wave function that evolves, and that's a pure, okay. But it's thermal.
Okay.
Yes.
Does it only work for if you have like a thermal state as your initial condition, or for any?
No, any initial state is fine. This is a convenient one, and it's often what you need. But it doesn't depend on the initial state vector. Now, preparing this is quite doable. Any other questions? Okay, so let's move on because I would like to continue with part 2. Okay, so having established the classical foundation for quantum dynamics. Now here we move to quantum simulations on quantum devices, and that now can be validated by those baselines. And here we have a new notebook, also accessible in the same web page. All of what this part is described, it corresponds to this paper, and that I will also share once we have it available. So why quantum dynamics on quantum computer is something we already talked about, which is this problem of the dimensionality of the Hilbert space and the exponential compression that you have with the quantum register. So this would allow to describe quantum dynamics where you cannot do it with classical computers, and exploit the native properties of quantum devices that naturally evolve according to the Schrödinger equation, even if you don't ask them, even if you don't pulse them on. If you prepare them in a given initial state, they will evolve in time according to whatever Hamiltonian they have, according to the time-dependent Schrödinger equation. So there is the possibility also of exploiting that native unitary evolution or non-unitary evolution also if they couple the transmission line without having to compile anything on them. That's a very hot topic of research at the moment, how to exploit native dynamics with native gates. And now, we're position part 2, which is this talk is in this, having validated that, before going into open systems. So now the core philosophy is now reframed for quantum simulations, but remains the same, with the same Hamiltonian, same observables. Now, instead of choosing that back end that happened to be the ODE solver on a classical computer or soft, now you launch a simulation on this quantum circuit. And that, you build a circuit, series of Python instructions that enables you to send a sequence of pulses to a quantum processor that evolves, the quantum prepares it and evolves it on a quantum circuit. So the back end is a detail of implementation. The methodology is the same, and the system is the same. So in this part, now the question is, again, solving these time-dependent Schrödinger equation when the system is pure, because we've just learned that we can also use it for mixed states, right? Because if it is mixed, you purify it, and then you implement the same approach. And the hardware supports only certain conditional and unconditional gates. So the question is, how are we going to implement that transformation with those gates that are available on that quantum device? We can talk about implementing this with Q modes or with qubits. Here I'm going to be focusing with qubits. We also published several articles on how to do this with Q modes. So there is a need for systematic decomposition that allows us to prepare the initial state and also the unitary that is necessary for evolution of that initial state. Very convenient decomposition is the Pauli decomposition, where you have an arbitrary Hamiltonian can always be written as a sum of Pauli strings, where Pauli strings are just tensor products of Pauli matrices. And the coefficients of that decomposition are simply the trace of that Hamiltonian with the corresponding Pauli string that you are computing the coefficient for. So you can always rewrite your Hamiltonian or any Hermitian operator in this way, as a sum of Pauli strings. And so this is an exact orthogonal basis, and also is sparse for physical Hamiltonian, so it's very convenient. So if you do that, now what you have is that for the time evolution operator, you have the exponential of minus I sum of this AIP sub I is T over H bar, right? But if T is sufficiently small, like here we divide it by M and we make M sufficiently large, then you can assume that all of these operators commute with one another. Because although the polystrings don't commute with one another, when you multiply them by this T over M, you get an error that is proportional to T over M squared that you can neglect. So what you can do is forget about that non-commuting property of a polystring, implement this and repeat it M times. And then you will have implemented and this is what we call trotterization, that is a terrible method because it requires very deep circuits, but formally is exact, numerically exact, and easy to implement, and is sort of the conventional way of doing Hamiltonian simulation, which is how this field calls quantum dynamics. For decades we've been calling it quantum dynamics, in science, Hamiltonian simulation. But it's about this, poly decomposition of the Hamiltonian and then trotterization in this way. So more steps gives you more accuracy, but deeper circuits. And in the time of noisy computers, you have to worry about those. So in general, you cannot do any realistic simulation on a existing quantum computer with this approach at the moment because you need thousands of layers of gates. But you can simulate those circuits, waiting for quantum error correction to fix the noise problem. Now, so if this is a way of doing it, how do you actually build a circuit that implements, for instance, one of those polywords? In this case, it's a polyword that has only Z polymatrices. It's a tensor product of 3 Z polymatrices. And you want to evolve the initial state vector with this transformation. So what you can demonstrate mathematically is that all what you need to do is to collect parity on an ancillary qubit. That means parity is how many ones you have in the state vector, because you see, when you have a state vector and with 3 qubits, in this case we have these 3 working qubits, and you apply Z, you see Z, if the qubit is in the state 0, which is 1, 0, gives you the same 1, 0 multiplied by 1. If the state is in 1, which is 0, 1, you apply Z, you get minus 1, that vector. Right? So the eigenvalue is 1 or minus 1. Parity counts how many minus 1s you have there. If you have an even number of minus 1, the parity is 1, is even, otherwise it's odd. Right? And the way you collect that is by doing this control knot onto the ancilla. You say, is this 1? So tell me this 1. Is this 1? Add 1. Is this 1? Add 1. So if these 3 ones are, then you get 1 plus 1 is 0, plus 1 is 1. So it tells you that it's odd. Right? So in that case, you apply a rotation on this ancilla, which is defined with an angle that is twice that tau. And then you uncompute the parity. And what you can demonstrate is that this ancillary qubit remains in 0, so you can repeat this as many times as you want. And what you have applied on these 3 qubits is this transformation. A little bit of magic. I lost part of my pointer, but hopefully will. Is this sufficiently clear? So this is the all Z time evolution operator, if you want. So how you apply this for an arbitrary poly word, for an arbitrary polystring, is simply you rotate those that don't happen to be Z to the Z direction. You see? So if you happen to be X, Z, X, then you apply Hadamard gate, transforms X into Z. Then the second one you don't do anything. For the third one you apply another X, because this one is also X. And then you collect parity associated after having rotated these qubits into the Z direction. And then you apply them again here to uncompute that rotation, so you don't modify it. So basically, this is the same approach, which is a rotation of an ancillary qubit, allows you a multi-qubit transformation with an arbitrary large number of qubits. So this is an example, X, Y, X, I, Y, Z. See, so X needs to be transformed into Z, that you transform with a Hadamard gate. I'm sure, you know what a Hadamard gate is, right? Yes. So, so for I, you don't do anything. For Y, you have to rotate it to the Z-axis. With that rotation, for the Z, you don't do anything. And you collect only from the qubits that don't have an I, right? So you collect parity, again, so that allows you to implement the totalization. You concatenate this with as many polywords as you have, and you're done. So here's the script on how to do this, how to build this circuit and implement a circuit for this transformation of an initial state. Now, in the general Hamiltonian, you have that, where is it now going? In a general Hamiltonian, you never implement this manually, as it is done here in the script, in the example, because Qiskit offers, black box functionality for doing all this automatically. So you just have to define your Hamiltonian as a sum of polywords with the corresponding coefficients, pass that into the Hamiltonian simulation, and that define how many Trotter layers you want, and builds a circuit for you. So this is all automated, and you can see how it is, how you can make use of that built-in functionality of Qiskit by running the script of QFlux. So what QFlux does is the poly decomposition, the circuit generation, totalization with various layers, and then the execution could be on a simulator or on the real device. If you have an API for your account of IBM Quantum from the same notebook, you can run on the IBM computer. So this is the script that you need to run. And this is how it looks for the automated Hamiltonian simulation, where you're building that set of polywords with coefficients, and you're composing the circuit associated with that device. So basically, this builds the circuit implementing each of the polywords that you're going to be concatenating, and appends it into a circuit that ultimately gives you the product of exponential of polywords corresponding to the totalized form of the short time step propagation of the total Hamiltonian. Now, if you want to compute observables, you have a couple of choices. One is with a Hadamard test, which is as follows. Imagine you have this wave function that comes out of this circuit after evolving the state, and you want to compute the expectation value of u, and u happens to be a unitary. There are also variations of these for non-unitaries, just for Hermitian operators. But if it is unitary, then what you do is the following. You pick up an ancilla, so you put one qubit more, you apply a Hadamard, and then you apply the conditionally with the ancilla to be 1, you apply the operator of the observable you're interested in. And if then you apply another Hadamard into the ancilla, and you measure the ancilla, and you repeat this measurement thousands of times, what you get here in the ancilla is the real part of the expectation value of that unitary. So you can actually demonstrate that analytically with that this is this average corresponds to the. So all what you need to do is to average. One time I have 1, another time I have -1. Keep measuring here in the computational basis. I accumulate all those measurements, and that gives me an average that corresponds to this expectation value. Again, you never make a measurement on these working qubits that correspond to the representation of the system, but you entangle those qubits with the ancilla, and you measure the ancilla. Another way of spooky action at distance, something that Einstein didn't like at all. And, okay, if you want the imaginary part, all what you need to do is to rotate the ancilla in minus pi over 2 before this conditional unitary. And what you would get here is the expectation value of the imaginary part. So this is one of the ways of doing it. This unfortunately adds to the circuit depth that you try not to increase the depth of your circuit. So this you will try to avoid this Hadamard test as much as possible, but this is a robust way of doing it. And when you're doing it with simulators, you don't care, because after all, the simulator is matrix vector multiplication, and we'll do it particularly if you have friends at NVIDIA like we do. So, but in real devices, you try to avoid this. So what do you do if you don't want to do a Hadamard test? We're going to talk about it in a second. But I want to give you the circuit for implementing this in that script, which is the script 232 from the second notebook, where you see that the implementation of this Hadamard test is very simple, because you just need to apply a Hadamard test into the ancilla and concatenate with the conditional unitary and measure the ancilla. You only measure the ancilla here. So, so here's the alternative method. If you want to avoid Hadamard tests, what you have is a method for describing the observable as a sum of polywords. Remember how to do that? It's the same as representing the Hamiltonian as a sum of polywords. All what you do is you have all possible polywords. Unfortunately, you have 4 to the n, so it doesn't scale well. But for each of those, you compute the coefficient a, which happens to be the trace of that polyword and the observable in this case. It's not the Hamiltonian, it could be any observable. So now you have the coefficients of that expansion of your observable in terms of polywords. So now all what you need to do, if you want to get an expectation value of that observable, is to get expectation values for each of the components of that sum of polywords. And then with a classical computer, you combine them, you average them with their corresponding coefficients. They happen to be the trace of the observable times the polyword divided by 2 to the n, is the number of qubits. So this is what is described here. You have an observable, it's a sum of polywords with the coefficients defined like this, and where these polywords are just tensor product of polymatrices and identities, and the observable is the sum of those expectation values for each of these. So in your circuit, instead of having to build in this overhead, all what you have to put here is the corresponding polyword after the state vector, and measure that polyword many times. That will give you the expectation value. Then you put another one, and so it gives you many circuits that you have to use, because for each polyword you need one of those circuits, but you don't have this extra depth of the circuit. Does that make sense? Is this too basic, or is fine? It's good? Okay, so for instance, one of the most popular approaches, I'm sure you've been discussing in the workshop, is VQE, variational quantum eigensolver, where you're trying to generate a state vector that minimizes the expectation value of the energy. So you want to compute that expectation value of the energy, so you write the Hamiltonian as a sum of polywords, and then for a variational state vector, you compute this expectation value for each polywords, and you combine, and you try to minimize that expectation value. So it's implementing this direct approach without using Hadamard tests.
Do you need to do a Hadamard test for each Pauli word in that case? Because you're computing the expectation value for each and then combining them?
Yeah, it depends on what you're doing. So if this happens to be not a unitary, you're right. You have to write it as a sum of unitaries that might be polywords, and do this for each polyword. But if this happens to be a unitary, you just have to write a circuit for this, and you compute it all at once. So it could be a trade-off. So in this example, for instance, you have the example of evolving a given state, and by totalization, given a Hamiltonian. In this case, I use a two-spin Heisenberg model because I knew many physicists like this one. And then you have the scripts for initialization, propagation, and measurement. And at the end, what you see is comparison to the baseline classical with a simulator quasar and with a real device. And when you make the probabilities of the outcomes, so in what possible states I can observe the final state vector after evolution, the correct result is you can only have it in the 0, 0 or in the 1, 1. But if you do it on the real device, you have some error, and also reports that sometimes you see it in 1, 0. What happens in the real device is that due to the imperfections of the poles or interaction of the qubits with the environment, what you have is something, the same circuit you encoded with your Python code, but some other gates are introduced at random, like a X gate. Once in a while flips the phase of one of the qubits, for instance, or a Z gate flips the bit from 0 to 1. So I said that in reverse. So, Z flips the phase, and the X flips the bit. So you think about your circuit plus these random gates that sometimes show up unexpectedly and flip either the phase or the bit of your qubit, and that's what gives you this result. So one thing is, you have to be aware of that, and also implement methods for correcting. There are ways of mitigating errors. So for instance, you can get these results and then run the same circuit with a benchmark for which you know what the output should be, and compute the confusion matrix that would correct for these errors. So that would be one way of fixing these errors. But that is a little bit of the workflow, and that these results are not failures. They define the operating regime of these devices and motivate the development of error mitigation. So now the question is, can you actually do more than 2 qubits? Can you scale this up? So here's an example with an n-spin Heisenberg chain where represents all kinds of problems in chemistry and physics. And you do the same thing, and you can compute, in this case, you can compute the survival amplitude. Something that I didn't mention is that Hadamard test that I described for computing expectation values of observables. You can also do the same thing with correlation functions. So if you conditionally apply the reverse of the time evolution operator to the state vector, you're computing essentially, you're uncomputing the evolution. So now when you compute expectation value, you're sandwiching the time evolved state with the unevolved state. And that is the survival amplitude that we are describing here. So that is with a script for implementing the Hadamard test for computing the survival amplitude. Survival amplitudes are great because if you Fourier transform this, you get the spectrum. So you can connect it directly with observables. So there are ways of doing the totalization more efficiently by trying to reduce the depth of the circuit, rearranging the order by which you apply these Trotter steps. And so combining steps, you can do for instance, you have this approach where you take nearest neighbors, but you don't couple these two. Then you couple these two. This is like the time evolving block decimation approach. And so this is the one approach for reducing the depth. This is another one approach. And in this script, we define how to implement these compact versions of totalization for the n-spin Hamiltonian. We can also implement the soft approach, as I mentioned, with these devices, with quantum devices, in the same way as we have the totalization between coordinates and momenta. For instance, if you are describing a system represented in a coordinate representation. Then you apply a circuit for the potential propagator, quantum Fourier transform, kinetic, inverse Fourier transform, and potential. And this is the code in script 240 for implementing this trotterization according to that approach that corresponds to this circuit. So you see it's a very compact code for doing that. And with this, for instance, you can have the script for evolving a proton across a DNA-base pair. So this is adenine thymine, and these protons sometimes jump from one to the other and they are transferred. And the description of proton transfer through this hydrogen bond is described by this potential energy surface. This happens to be an important problem beyond a simple example to demonstrate that we can implement these methods on realistic models. Watson and Crick described this process of proton transfer when they published the structure of the DNA. And they say that in the moment of DNA replication, when these two strands separate, if the proton is in the wrong place, then leaves a base with affinity for a wrong base, instead of the corresponding base, for the wrong base. So the process of proton transfer at the moment of replication might lead to mutations, because now the replicated DNA might have attached the wrong complementary base. And that might happen actually when the DNA is hit with light, because in that case you have this hydrogen bond complex excited, electronically excited, and this barrier is smaller when it is in an electronic excited state. So that's why they mentioned this is a problem that may be relevant to skin cancer. Anyways, for this tutorial, the question is whether we can simulate with a Q-soft approach, so the soft approach implemented with this quantum circuit. And in fact, this is what you will get if you run the simulation as compared to the baseline. And so this is the KISS kit, and that's the corresponding baseline based on the ODE solver, showing that you can, in fact, reproduce exact quantum dynamics with this approach. Now, the takeaways from this part is that Hamiltonians are just representable in terms of polystrings, and for each of those polystrings you can build a circuit. And the results of classical methods can guide the development of these algorithms, because QSoft is nothing but a quantum circuit implementation of the method that we demonstrated already on classical computers. Validation is never negotiable. Always make sure that you can show that your setup and implementation reproduces at least one problem that can be solved analytically or with a baseline that is reliable. And QFlux provides the full workflow for that. So that essentially completes the second part, and the next steps would be state preparation, open quantum systems, and variational approach. And I see you're all a little bit tired by now, so you may need a break. And in the second half, since I cover only two, you can pick 2 out of the 3, because I don't think we will be able to cover everything. And this one is a little bit heavier, but it's very interesting. So this one actually allows real implementation on NISQ devices, because variational approaches are very effective. So how to do open quantum systems and how to do it variationally, I think would expose you to something that you're usually not going to be exposed otherwise. Anyways, we'll continue after the break.